Hi everybody, welcome to my channel, Theoretical Physics with Mark Weitzman. I'd like to continue today with the second part of the video. This will be QFT review blog video 11.4.2023. We'll be covering material from Z's QFT nutshell book. On repulsion and attraction, scalar, vector, and tensor. This is part B, vector. So basically in this part we'll be doing electromagnetism, but we're going to do it with a massive photon, so we don't have to worry about all these technical issues of gauge invariance and everything. We'll take the mass to 0 at the very end. Let's start with the Lagrangian for electromagnetism. But with a massive photon. And avoid gauge invariance issues. Eventually M will go to 0. We'll see if we get a good theory. So our Lagrangian is -1/4 F mu nu plus 1/2 M squared A mu plus A mu J mu. A is of course our vector potential, and this should be familiar to most of you. This is the usual term, the field term. This is the coupling of the electromagnetic field through a charged particle. This is J is the source. And if we were doing like some kind of spinor theory, we might have something like psi bar gamma u psi as our source term. But we're not really interested in worrying about what our charged particles are, and they may even apply to scalar charged particles. So let's not worry about spinors for now. Now the sign of this term, sign is determined, and this is the massive photon term. This is the field term. The sign is determined by requiring, we'll spell that, the kinetic term coefficient the partial of 0 of AI squared to be positive. And if you use the definition of the tensor and expand it out in here, you'll see that it will be positive, because when we raise or lower a spatial index, we get 1 minus sign. That will cancel out the minus 1/4 sign. And as usual, as we should always do in electromagnetic calculations, we assume a conserved current or source. So we get the usual, doing the same thing that we did in part A. We have z is equal to the integral dA e to the I, the action of A. And this is defined to be e to the I w of j. And the action, again, as usual, is defined to be the space-time integral of the Lagrangian. And again, we'll do some partial integrations to get it in sort of a matrix form. Now, to evaluate this path integral, using our usual Gaussian formula for integrals and quadratics, we need to find the inverse of the operator, this thing over here, in square brackets. So we're looking for something like partial squared plus m squared g mu nu minus the partial u partial nu d nu lambda. In the scalar case, the propagator didn't have any indices because the exchange particle was spin 0, but now we're having a photon exchange, so we'll have a one index from where it starts and the source, and the another index for the sink, so we'll have two indices on the propagator. And this should be equal to del u mu lambda del 4x. Okay, so the way to solve this is we solve this in momentum space. And I'm not going to do it for you because I'm sure all of you have done this before, but you can, it's kind of routine and you can certainly verify the answer. So we're going to get the massive vector boson propagator. Hold on one second. I wrote meson in my notes. I meant boson. D nu lambda k is equal to minus g mu lambda plus k nu k lambda over m squared divided by k squared minus m squared. Very important, but also weird formula. If you look at the limit as m goes to 0, it seems part of it blows up. But it's not a problem because this will always couple to conserve currents, and we'll end up getting, as we saw earlier, this key equation. We're going to end up multiplying we're going to end up killing these this term by coupling to a conserved current. So and the conservation condition in momentum space is k mu j mu k equals 0. So when we couple this to j's, this term will go to 0. And evaluating the path integral using this exactly as in the scalar case, we're going to get, this is a very important formula, wj is equal to 1/2 the integral of d4x over 2 pi to the 4th j mu k star 1 over k squared minus m squared plus I epsilon j mu k. Now, just looking at this, what happened is that these terms went away, basically. And the minus sign here canceled the previous minus sign that we got in the scalar case. Now you might argue, you might think, what happens if we use the opposite metric, if we use the East Coast metric instead of the West Coast metric? Well, it doesn't change anything, because if we use the East Coast metric, that previous minus 1/4 would become a 1/4. So that's not what's going on. But we do get a positive sign. So now we have a positive energy. And an attractive force. Between like particles. I'm sorry. Positive means a repulsive. That's what we wanted. Opposites attract, likes repel. So the way to get, the simple way to get the opposites is we write the current as J mu equal to J mu positive minus J mu negative. And if we substitute in here and here, we'll find out that opposites will have a negative energy, and therefore they'll attract, and likes will repel. Now you might think we could do that in the scalar case also, but we're not talking about charge in scalar cases. We're talking about neutral mesons. There's only one, there is no charged, there are charged mesons, but that's charged electromagnet. If we just consider mesonic charge, we're just going to have one thing. So, for a scalar case, we don't have any positive and negative mesons, and for electromagnetism, we do. Okay. Now there's another way. I'm going to derive this. Let's derive this result a second way, because that's how we will do it in gravity, because we're not going to do the whole theory of gravity with the Lagrangian and everything. Then we have to get into a lot of general relativity. So the idea is that the propagator in QFT is essentially, we have a denominator. The denominator is always k squared minus m squared with the West Coast metric. And the numerator is basically, we start out with one polarization and we go to another polarization. You know, we're admitted with one and we're absorbed with one. So again, the path integral, the whole concept of path integrals is we look at all possibilities, all paths in space-time, and now we're looking at all possible spins. So D, not worrying about what the indices are right now, it's always the sum of all possible spin polarizations. And this concept is really developed real nicely in the book. It's an old book, but it's still very good. Leptons and Quarks by Hazelin and Martin. Now, for scalar, spin 0, the numerator is just 1. You know, there is no spin, so it's just 1. It's only one possibility. For a vector boson, spin 1, the numerator is the sum and A equal. So we have three polarizations. You might be used to seeing, like, when we have a massless photon, we have two polarizations perpendicular to the direction of propagation. So it's transverse. But if we're doing a massive vector boson, we also have the longitudinal polarization. So we have three possible polarization vectors or tensors. And A gives you which one of the three, and the nu and the lambda are the space-time indices, and K is the wave vector for propagation. Current conservation is expressed as again, this is in momentum space. Now, using Lorentz invariance, I'm going real fast here because I think many of you have seen these arguments. It can only depend on G nu lambda. We need two indices because we're going from one to the other. That's the nu and the lambda. So it can depend on G nu lambda, and the only other thing we have available is K nu K lambda. Make it dimensionless, divide by m squared. Now, if we evaluate it actually has to be proportional. Using this this condition, it has to be proportional to G nu lambda minus K nu K lambda over m squared. And if we evaluate this in the rest frame, So k is equal to 0. And we put nu equal lambda equal 1. This will fix the overall constant. Fix the overall and the crucial sign. And we find sum over A we'll just find this object now, capital G, is equal to minus and this is exactly what we had before. This is like the crucial minus sign. Okay, so that's the end of this video, and now we're going to go on in part C. We'll use this technique to show that gravity is attractive. So again, thank you for watching, and I'll see you in the next video.